Hi, my name is Williams and I'm going to take you through exponential binomial expansions. Let's say you are given something like this, m plus n all squared. This is what we are calling exponential binomial expansion. We are calling it exponential because of the exponent 2, and it is binomial because it involves two terms, m and n. Let's say you have something like this to handle. How do you expand it? Let's start. So we are given m plus n all squared. Let's apply the concept of area to explore how we can expand this expression. Let's say you have a square with length m. The area is equal to the length times length, which is m times m, which is equal to m squared. Let's say you have another square with length n. The area is equal to n times n, which is equal to n squared. Summary 1. We saw that when we had a square with length m, the area was m squared, which is equal to the length times length, which is m times m. We had another square with length n. The area was n squared, which was n times n. Now take a look at this. Activity 1. Can you think of any shape that will give us an area of m plus n all squared? Remember, when we had a square of length m, we had an area of m squared. And when we had a square of length n, we had an area of n squared. Now, how do we get a square that will result in an area m plus n all squared? Take a look. For us to get an area of m plus n all squared, then the length of our square should be m plus n. This will give us an area of length times length, which is m plus n times m plus n, which is equal to m plus n all squared. Summary 2. We have seen that when we have a square with length m plus n, we get an area of m plus n all squared, which is equal to length times length, which is m plus n times m plus n. Now look at this carefully. If the shape has an area m plus n all squared, it means that the shape can represent m plus n all squared, and m plus n all squared can also represent the shape because the shape has an area m plus n squared, or m plus n squared is the area of the shape. And we have seen that it is equal to m plus n times m plus n. So if we cannot even expand m plus n times m plus n, and we are able to expand the shape, which is equal to m plus n times m plus n, then the expansion of the shape should be the same as the expansion of m plus n times m plus n. By expansion of the shape, I mean breaking down the shape into pieces. Now let's open up the shape as an expansion of m plus n times m plus n. Let's go. So this is our shape, and I can see 4 sub-shapes within our shape. Let's look at it. 1, 2, 3, and 4. So if we are to cut this shape into 4 pieces, we are going to have 4 sub-shapes. I mean 4 small shapes coming together to form the bigger shape. So 1, 2, 3, and 4. These 4 shapes come together to form the bigger shape. And so when we find the area of each of the single small shapes, when we put them together, the area should be the same as finding the area of the bigger shape, because it is the same bigger shape that has been splitted into 4 sub-shapes. So the area of the bigger shape is still m plus n, or squared. Now let's find the area of each of the single shapes that come together to form the bigger shape. M squared, because the length is m, for figure 1. N times m, because the length is m and the width is n, for figure 2. N times m, because the length is m and the width is n, for figure 3. And then n squared for figure 4, because the length is n. We are still equating the two sides of the equation, because the right-hand side is an expansion of the left-hand side. They are still in figures. M plus n squared is equal to the combination of m squared, nm, another nm, and then n squared. So the figure is still m plus n all squared, that is a bigger shape, which is equal to m squared plus the second shape, which is nm, plus the third shape, which is also nm, plus the last shape, which is n squared. Now let's pull out their area to form our equation. M squared plus nm plus nm plus n squared. So we have been able to pull our equation from the single shapes, that is the expansion of the bigger shape. Now m plus n all squared is equal to m squared plus nm plus nm plus n squared. But we can see that we have 2 of the nm's in the equation, so we put them together, and that gives us 2nm. So we have m squared plus 2nm plus n squared, and that is our answer, which means that when we are given m plus n all squared to expand, it is equal to m squared plus 2nm plus n squared. Now let's look at summary. Number 1, m plus n all squared. We saw that it is equal to m plus n times m plus n. And we also saw that when we have m plus n all squared, the answer is m squared plus 2mn plus n squared, which means that we can equate the right side of the two equations, and that should also be the same. Therefore, when we have m plus n times m plus n, it is equal to the multiplication of the first terms of the two binomials, which is m squared, plus m times n, which is the multiplication of the first term of the first binomial and the second term of the second binomial, which is m times n, which is mn, plus nm, which is the multiplication of the second term of the first binomial and the first term of the second binomial, which will give us nm, plus the multiplication of the second term of the first binomial and the second term of the second binomial, which will give us n squared. So we simplify our equation to get m squared plus 2mn, that is a combination of mn plus nm, which is 2mn. You can also make it 2nm. The positions do not change anything, plus the last term, which is n squared. And that is our answer, which means that anytime we have m plus n all squared, our expansion should yield something like m squared plus 2mn plus n squared.